Hello learners, welcome to today's seminar about the battery production and in specific in Module 1, the electrode process and production process for battery cells. My name is Christoph Lienemann. I work as an engineer and consultant in the EV and battery space since more than 15 years. I have been involved in many projects, both on industry and research side. Worked around the globe in different projects with large and small players in the battery industry. And since, basically the beginning, I'm really intrigued with the topic of batteries and battery production. For me, the future of mobility, the future of our world lies in the electrification of a lot of product and specifically the mobility. And here the batteries, of course, play a significant role in electrifying the transport, electrifying the phones, electrifying everything else to have portable batteries and energy with us. So today we're going to look into how the battery cells are produced, and we're going to divide that into three major steps. And in our first module here today, we're going to explain you how the electrode of battery cells are manufactured. I will explain you a little bit later what are electrodes and how they are connected to the whole battery, and then we will dive into a deep dive of battery cells and production processes for those electrodes. We will also look around different technology alternatives and give a small insight in what are the challenges, the quality parameters in those processes. Of course, this will be very technical at some point, but I try to make it very interesting for you so you have an understanding where that might play a role for your career, for your approaches into the battery world. Please don't hesitate also to let us know if you have questions, some ideas how to make that better, how to integrate that in your daily life. We would love to come into a discussion with all of you. Furthermore, I would like to encourage you to look beyond that presentation today and look around reading materials about different topics. I will give you some small suggestions in the end of the video where you can dive in a little bit more in detail, where you can broaden your knowledge and also deepen your knowledge in the battery production world. Why this is important for you? Because I think especially where there are a lot of raw materials we need for battery production, and as well as a lot of available energy and upcoming industries. I think here we all need to work together, broaden our knowledge to best implement those technologies right from the start. So we want to create a strong workforce in your country, in your region, to make sure that the battery production challenges are met all over the globe. Furthermore, I would like to connect the different networks around the globe and work together on optimizing production processes of batteries. For me, that's super important, and I highly believe in a diversity of teams, and I would love to teach you a little bit of my knowledge in the battery production world, but also I would love to connect to you and learn more about you. So happy to find me on LinkedIn, Christoph Lienemann, working at Motion in Aachen, Germany. So connect, reach out, happy to always broaden my network. But without further ado, I would love to dive into today's presentation and give you a small overview about what we are going to learn today all together. So pause the video if you want to repeat things. Also, feel free to reach out and let's start all together. Let's learn about battery production processes. So in this video, I will teach you about how battery production is structured. We will dive into the electrode manufacturing of a battery cell. You will learn why the electrode is basically the heart of a battery cell, where energy is stored and released. So why the process of electrode production is also very critical for future production processes in the value chain. I would say it's the most critical process and the most secretly kept process in battery production. So please pay attention to these processes because it's really a valuable insight we're going to share here with you. Furthermore, we will also explain a bit about the requirements of the production processes and the environment condition those production processes need to happen in. Last but not least, we will give you an understanding of what are the critical quality characteristics of those electrode production processes. And furthermore, you will learn what an everyday process of baking and drying bread, for example, has to do with battery production. So there are a lot of processes which you might have seen in small, scaled up to industry scale, like mixing, like drying, like coating, for example. So stay tuned and dive with me into the exciting world of electrode production in the battery. Let's get started. So before diving into the production processes, I would like to explain you how a battery cell is normally constructed. And we normally have four main components, which are the anode, which functions as a negative electrode, typically copper foil with a graphite coated on top. Then we have the cathode, the positive electrode, normally aluminum foil with the different active materials where also the name lithium-ion battery comes from. Then we have a separator separating both the anode and cathode, making sure there's no direct contact. It's normally a porous material which allows the electrodes to flow within the electrolyte. So normally we have a liquid electrolyte which allows the exchange of the electrodes between anode and cathode. We don't want to explain you too much about the principle how a battery cell functions here. This you can see in a different seminar. Here it's about the production process. And for the production processes, it's super important to understand there are different cell formats. So the first cell format is the pouch cell format. A pouch cell is also called coffee bag cell because it's basically a similar material like where your coffee can be stored. It's an aluminum foil allowing very high flexibility, but also, of course, difficult to handle within the production process. Then we have the round cell or cylindrical cells, normally a tubular shape and highly standardized in its size. So we have different formats, for example, 18650 or 21700, which are references to the geometry of the battery cell. So here we can really use the full volume of the battery, filling it completely with active and passive material, the anode and cathode, and the electrolyte. On a pack level, of course, putting them together, there's volume lost between those tubular shapes. So there's always a pro and con using the different cell formats. And the last cell format is the prismatic cell, which is a rectangular shape, allowing for very strong, secure battery cells to be produced. So all of those cell formats have advantages, disadvantages. For me, there's no favorite, but of course they all required different production processes. And we're going to look at that in detail here in a little bit. So let's dive into the production processes and let's look how the battery cell is really produced and how the different production processes are all interlined. So, how is it produced? Here you see an overview about the different production steps of a battery cell and its follow-up processes to produce out of those cells battery modules and out of those modules battery packs. Today we're going to focus on the first step in the electrode production. So typically the battery cell production is divided into three main areas. There is the fabrication of the electrodes with the mixing, coating, drying, calendering and vacuum drying process. Then we have the assembly of the battery cell. Depending on the format, there's a winding or stacking of the electrolytes. Then there's a filling of electrolyte in the battery cell, a sealing of the battery format, and then also some quality production issues. Later on, we have the cell finishing, which is normally a formation and aging process where we first activate the battery cell with its first load. So the important SEI layers within the battery cell can be created. I will explain that in the third video of this series and explain you exactly what is an SEI layer and how it's going to be produced. So after that, we finish the battery cell production and move over out of those battery cells, creating battery modules, connecting them electrically, but also with different security measures like temperature sensors or voltage sensors to make sure our battery is running correctly. Normally, we also integrate cooling systems, a housing for mechanical safety, and other important measures. Those modules then are stacked together into a pack where additional electronics, for example, the battery management system, is added, and then we have different electrical connectors, safety measures, but also thermal management systems, and also a lot of mechanical support structures and security measures, and normally also protection from water or external influences in the battery. So all this is happening in the module and pack production, which is explained by my colleague, Mrs. Dr. Ueda, in a different video. Today, as I said, we will focus on the first production process. And why I think this is super interesting and important, because here everything starts, and everything starts with raw materials. So we start basically at the very beginning of the battery production, bringing different raw materials to the battery production facility. And you can imagine copper foils, aluminum foils, so typical materials used here, but also, for example, cobalt, mainly coming from Africa, but also manganese or nickel, which is also mined in continents like Africa, but also South America, Asia. And of course, this is a very crucial and important factor for the battery production. Hence, I think it's super interesting also for all of us to take a deeper look into those production processes. Also, I want to mention that all those production is normally happening in a very controlled environment. So you want to have clean rooms, dry rooms, producing those electrodes and making sure you have little to none contamination into your battery production processes, because it's very critical to produce the battery very clean and without any external dirt or particles going into the battery cells, making sure it's also safe to use the battery over the lifetime. So looking at all the production processes would be interesting to get your feedback on where do you think the most costs are generated here in the production process. Is it the raw materials, or is it the production of the electrodes, or is it the assembly of the batteries, or is it the formation and finishing of the battery cell? And I would love to keep that question in mind, and we're going to answer that at the end of video 3 or of the lecture 3 about finishing the cell production. So ask yourself, what would you think how those costs are generated and what is the most important and critical factor in the battery production? So let's dive into the electrode production in detail and let's look how the first process, the mixing, looks like. And the mixing is part of the value chain, as you see here, but let's not long talk about it. Let's dive into the mixing directly. So the first process of the electrode production is the mixing. Here we bring together the different solid raw materials, add some water, for example, or different solvents to create a liquid paste, which is also called slurry, which is then coated onto the metal foils, on the copper foil for the anode and on the aluminum foil for the cathode. And typical compositions for the anode can be the active material, which is the graphite. Normally around 90 to 95% of its weight comes from graphite. The graphite can be both natural and synthetic. Then we normally have a carbon black structure as an additive for 5%, and then a solvent. The anode can be water-based, for example, with deionized water, and then we have different binders and additives depending on your formula. Some you see here displayed on the slide. For the cathode, That's actually where the name lithium ion comes from. We have an active material, in this case is an NMC, nickel manganese cobalt based formula, and that is mixed then again with different solvents and additives, here in this case NMP based solvent with binders like PF and DF in this case, which is around 5% of its weight. So as a cathode and anode are mixed differently, we normally want to have completely separated process chains for both processes. So the anode production happens in its own area to really avoid contamination, and also the cathode happens in own machines, equipment, and lines. So to really make sure you have separated processes here. They're also very different and they react different, for example, to moisture water. So NMC, the higher you go with your nickel part, the more sensitive to water it is, and to really avoid any particular contamination here in the processes, you want to make sure it's happening in a really clean environment. Also, you want to make sure that it's very good mixed. So you normally have very good mixing machines, which are active mixers, turning both the vessel, but also then the mixing tool inside the vessel, and leaving it really mix for a few hours, and making it a very even slurry to avoid any agglomerates in the slurry. So if you think about the analogy of baking a cake, here you put all the ingredients in your kitchen machine, and of course you want to use the kitchen machine to create a really homogeneous dough, and make sure there are no crumbs or clumps within your dough. So in industry, for the battery, normally we have mixing times from 20 minutes to up a few hours, making sure there's really a good even dough or slurry without any agglomerates. And we have different processes, alternatives to do that. We have rotary mixers, as you see here in the picture explained, planetary mixers, which are allowing a little bit more continuous process flow, centrifugal mixers, but also extrusion mixers, really being able to create a full continuous flow directly to the line, whereas as the process you see here would rather be batch based, and creating one big batch of slurry or dough to then coat on the electrodes. After the mixing, the slurry we just created in the mixing process is then coated on the electrode foils. So the anode slurry is coated on the copper foil for the anode on a separate machine, again in a separate environment, and then we have the slurry for the active side, for the positive electrode, coated on an aluminum foil on a separate machine. So then the foil is coated with a slurry using different applications. Most of the time we have a slot die here coating the slurry, which is pumped out of the batch process directly to the foil. And then the foil is either coated continuously or intermittent with stops, depending on the cell format you want to create. Generally, there are ways to coat the foil on one side, then turn the foil again and coat the other side, or there are also processes where we simultaneously coat both sides of the foil. In the end, we want to make sure both sides are coated and both sides are coated equally, and there are also no breaks between the coats on different positions on both sides of the foil. Then the coat is then also transferred to dryer in the next step, but let's focus here a little bit more on the coating itself. So we normally use the foil then of big coils and feed them to the machines, where then it's directly coated on the foil. The foils can have a pre-treatment and be prepared for the coating to ensure better adhesivity for the slurry, but it is not necessary. Then we have measures to control the thickness of the coat, making sure we create an even surface of our coating through the whole foil. We also can control the surface of the slurry, making sure there are no agglomerates again. It's evenly coated. There are no particles dropped into the slurry. And yeah, making sure there are no blowholes and assuring a good quality before going into the drying processes. Normally those machines are huge because of the following drying process, but they need to be also very precise in the coating thickness and making sure there are no imperfections in the slurry. So we have coating speeds from 35 minutes, can be even up to 80 meters per minute in the industry. And of course here creating the throughput of the whole line, as this is a very crucial and a very highly controlled process. Here you set the quality of the battery for all the later stage. So from here on it can only get worse. So you want to make sure that your battery here, your coating process is really good, and the combination of your mixing, the secret formula, the secret ingredients for your battery is really transformed well onto the electrodes. And those two processes are, I think, the most crucial ones in battery production for quality-wise. So here you get a good insight in potential errors you can create within your coating process. So you see in the first overview potential agglomerates which could still be visible in the slurry after the coating processes. Also, sometimes you leave holes in the coating, so there's no constant material flow in the drying or coating process, so leaving those holes, and of course you want to avoid that. Also, your edges of the coating can be very faulty, more like waves or having holes, or are very uneven. So in all this you want to control typically with a camera vision process, and also making sure to keep up with the high speed of coating which is necessary to meet the production rates in your production process. So typically the foils are very thin, few micrometers thin also only, and on top of that you have the coating thickness which can be up to 250 micrometers on the wet stage. Of course after drying that would reduce a little bit, as you see here. Another interesting factor to measure is the viscosity of your slurry, and making sure you can have really the right throughput through your slot die, and avoiding things like this here, for example, with the missing material during the coating processes. So also this is happening in a clean room environment normally. Sometimes you have also the slot die housed in specifically if you, for example, handling high nickel active material for the cathode. Also, if you're handling NMP solvent, you want to make sure that you have a controlled environment to avoid people being contaminated with this harmful material during the production process. Once coated, the electrodes are wet with the slurry, and due to the solvent can be either NMP or water-based, depending on the chemistry, of course. A drying is required to evaporate the solvent, leaving behind porous solid electrolyte layer on the foil. And it's very critical that we get the solvent out, and to avoid any moisture within the cell, to avoid any contamination, but also making sure that it doesn't dry uneven or too fast, to avoid cracks or any other problems for the coating itself. So also here we have different methods, or a combination of methods which can be applied. Typically in the industry we see long convection drying, so hot air blowing over the foil in an oven-like structure. It's normally a very long tunnel in the production processes, using a lot of energy, of course, also. Sometimes we can add lamps or infrared light or lasers directly to have a pre-coating or pre-drying, for example. Sometimes we have also air flotation suction dryers, so the foil floats through the process itself. But yeah, we want to basically avoid touching the foil too much or at all to avoid any imperfection in the slurry itself. So the foil travels then through the oven, and yeah, the heated part of the oven, which normally has also different temperature profiles to ensure that the solvent also from the bottom layers gets out distributed evenly and dries the whole slurry, not just the top layer. If you dry, for example, too quick, or just too slow, also to avoid any delays in the process itself. And those different temperature profiles are normally designed by a chamber-based or modular design of the dryer, allowing different chambers with different temperature profiles. And you want to make sure that in the process you also recover the highly flammable solvent like NMP, for example, in a special system to reuse it again, but also making sure it doesn't reach the environment just unfiltered. Furthermore, yeah, the foil needs to be cooled down to room temperature in the end again to be used for the further process steps. Depending on if you coated your foil directly on both sides or just single-sided, you want to also make sure to handle the foil, the bottom side of the foil correctly. So using, for example, airflow to avoid any touching of the both coated sides. And the drying requires, of course, high temperatures from, depending on the chamber, 80 to 150 degrees Celsius. And of course, like this, it's also high energy intensive process. So here we really create a lot of energy in the production process. And this is, of course, reaching the footprint of the battery production significantly. Also, we want to make sure that we still have a control over the wetness to avoid any contamination again with water of our slurry. And this can be done by different quality parameters and ultimately also regulating the speed of the foil going through the production processes. So normally the length of the dryer is also defined by the temperatures, by the temperature profile and required thickness or wetness of the slurry after the drying process. So, of course, I mentioned already that the drying consumes a lot of energy. Imagine now this 80, 100 meter long oven running 24/7 in a gigafactory. This is a building block which costs already millions of energy per year. And also here, of course, the first reliable source of energy, but also cheap source of energy is super important to reduce production cost and can be a chance for upcoming regions in the world to locate battery production here and allow local manufacturing directly. And I will leave you a little bit with this slide where you can see the different technologies used to dry the electrode, because I think it's interesting to understand the differences, and it can be also a combination of both. So for example, you can be using a laser based drying and add a convection drying process afterwards to really make sure the slurry is dried completely, but reduce the energy impact by just having a much shorter convection drying system after the laser drying system. So the industry is working on ways to reduce the energy consumption significantly because that's a high cost factor and of course also an important factor to consider for the footprint of the battery production. So please take a look at that slide, try to understand the processes, and then we will give you a small example for a laser drying process and a small video where you can see how it looks like in the production process directly. So on this video here, you see an example of a laser drying process of, in this case, the anode, which is the coated copper foil. In this case, we used a water-based solvent and slurry. And you see the water here evaporating when the laser is applied, making sure the slurry is pre-dried before going then, in this case, also to a convection dryer, but just, of course, reducing the necessity for a long oven, but rather having a much shorter process to ensure the right dryness of the slurry after the drying process. This is equipment here used in our facility in Aachen. It's a little bit smaller than an industry scale facility, but the principle is very much the same. So you see the intermittent coating where there's a break in the coating. We use also a slot die for our coating here, and then we apply a laser for the drying process directly to the battery cell. So you see the water here also evaporating on the foil as it comes out of the slot die coating and goes into the convection dryer. So after the slurry is mixed and then coated on the foil from both sides, that's important, and the slurry is dried, the foils go to the next process, which is the calendering. But once again, I want to highlight that the first three processes, the mixing, the coating, and drying, are the most important processes in this step, and define really the quality of the battery cell and are kept secret from a lot of battery cell manufacturers, and even kept out of the production sometimes, where you just buy the coated electrodes and start the production processes from afterwards, because it's so secretive, and a key knowledge of the players to make it right, and reduce their scrap rates here significantly, as it's very easy to do something wrong. But also the calendering is defining the quality of the coated electrode foils significantly. Also here we normally use two different calendars for the cathode and anode to avoid any contamination. So what does it mean, calendering? So the calendering is basically pressing the foil through different rolls. You can see here schematically displayed in this process. So you feed the foil, and then first the foil is discharged electrically by brushes or by an airflow, making sure that all the static load is gone, and then they are pressed by a top and bottom roller with a defined pressure through the whole length and width of the foil. So they define a precise line pressure, so there's only a very thin spot where they really press, but by feeding the foil through the calendar, it's making sure it applies the pressure everywhere evenly. And after calendering, normally you have also a cleaning process, making sure to take out all the particles which are maybe still there, and then roll up the coil again, preparing the electrode coil for the next production processes. So typically the line pressure defines the porosity of the coated material, and that influences ultimately, subsequently, the wetting properties, which become important in the electrode assembly, where you add the electrolytes. So with this, the energy density of the cell is highly impacted. So you want to assure a certain porosity, making sure the electrolyte can fit into the slurry here, but also you want to make sure that the slurry is on the right height. So that's exactly precisely the height you're targeting for your geometries mechanically, making sure it fits in the cell if you add several layers of that anode cathode separator sandwich, as we called it in the beginning, on top of each other. The cleanliness of the rollers and the process is very crucial, because you can imagine if you now press a particle with the line pressure, it has a huge impact, and you want to avoid any particles, any contamination within the process. So technical cleanliness here is crucial for a successful process. Typical values here to maintain a certain line pressure could be around 2,500 Newton meter per Newton per millimeter, but also calendering speed normally is quicker than the coating speed. So normally the calendars work quicker as the coaters. So you can normally use one calendar, one slitter here after the coating process. To just give you an understanding on how much impact the calendar has, the porosity can be reduced from around 50% after the drying process by the calendering to around 20 to 40%, and that's defined by the gap width you leave between the two rollers and the pressure you create. Sometimes you also want to preheat sections of the roller, and using hot rollers, for example, depending on the system concept. And yeah, ultimately, you can basically impact the ductility with heating the rollers. On this side, you see there's a example of a calendar machine. Looks quite fancy with a lot of rolls and process technology. And you see also here a video, sorry for the German subtitles. So you have the closing of the calendar, then the pressure impact on the line pressure. You have inline measurements of the thickness, and then ultimately applying the pressure throughout rollers here. And that gives you a good understanding, I think, of the process. I think a video always helps to understand it more in detail. So I will leave it running for a little bit longer. And please also take a look at the typical process parameters you see here displayed on the right. So after we now mixed our raw materials, coated them on the electrodes, dried them, and pressed them in our calendar on the right measures and porosity, we still have very big coils, if you can imagine, up to, for example, 800 millimeter width. But for cell production, we actually need much smaller formats. So typically, we want to cut the big coil, the mother coil, into smaller coils to feed them directly into production, depending on the size of your battery cell. Could be, for example, that you split up the 800 millimeter width wide coil into, for example, 8 100 millimeter coils. And that can be done by either using knives, rotating knives, or by using lasers. Both have disadvantages and advantages. I will go into a next slide where we explain the difference between both processes. But important here, again, you want to have a precise cut, making sure you have no impact from the material, for example, while cutting on the coating itself. So you want to avoid any particles. So normally that's also happening then with an additional cleaning process, making sure both sides of the foil, all impurities or particles are, for example, with a suction system, are taken away, and any leftover is avoided to avoid any short circuits within the battery cell later on. Then the smaller coils are rewinded again onto smaller coils and then used in the next production process, normally directly transported to the vacuum drying, which I will explain in the next process step, to avoid any additional moisture uptake of the sensitive anodes and cathodes in the later on projects. So they might be even stored directly in a dry environment or directly put in the drying process itself. And here in this slide, you see the main used alternatives for doing the slitting process of the mother coil into the smaller coils, and that can be either used by mechanical slitting, so you use blades, which basically circular blades cut the material right away while the foil is fed through, or you can use lasers to do the cut instead of the blades. Typically, of course, the knives, the blades wear out over time, and with increased wear produce more uneven cuts, so they need to be replaced, making sure they are replaced before there are any imperfections brought into the battery cell. So typically you can introduce more wear-resistant blades, but also making sure with control of the process to detect the wear right away or potential particles right away and avoid having them fed into the follow-up processes. For the laser cutting, the disadvantage is you have an additional heat applied near to the laser cut, so you want to make sure that that has no impact on your coating in the later on. Of course, you don't have any wear due to no physical contact, but using rather the laser, you have a much clearer cutting edge and a lower risk of particle contamination. So both can be used in industry, both have advantages, disadvantages. Ultimately, you want to make sure that you have a very good accuracy here, and you want to avoid any particles in the follow-up processes. So yeah, the slitting, I think, is important. It's important here to avoid, again, any imperfections as in most of the battery production processes. So cleanliness here, again, is key. So if we compare the two last processes, the calendaring and the slitting, to our baking analogy, you can imagine using this roller to really make the dough a little bit thinner, like in the baking process, and then in a second step really cutting the dough into smaller pieces to prepare them for baking, basically. And that's happening in the slitting process. So if you have cut several doughs, you know how important it is and how difficult it is to cut them always to the right size and making sure they fit what you want to bake. And also it can be very tiring, of course, to do that 24/7, making sure there's no wear in your muscles or in your knife you use. So use that analogy again and compare it to the baking process. So yeah, I think you can imagine the level of precision both in the rolling calendaring process, but as well in the slitting processes. And a short question: why do you think we want to move the slitted coils right away into a dry or vacuum dry environment? Why do you think this is important? And we're going to look at that in our next process step with a little bit more in detail. So after the calendaring and slitting, normally you transport your small coils into a vacuum drying process. And you might wonder why after the first drying process I need to dry again. It should be dry, right? There's no additional moisture or water added. But you want to make sure that there is no moisture, no water within your battery while you assemble it. Because those electrodes are assembled in the follow-up process where they meet the sensitive electrolyte, which doesn't like water. You want to make sure there is no water brought into the production process. So you have a very precise and more accurate and more dry vacuum drying process to really get the last tiny bit of water out of your battery, out of your battery electrodes. And to avoid really creating hydrogen fluoride or fluorane, the HF, which you don't want to create, which happens when the electrolyte meets water. So that's the reason for this production process. Most of the manufacturers implement it before transferring the coils into a very dry room. This is a special infrastructure where you work under controlled environment with a very low dew point to avoid any additional water which can be brought, for example, by the breath or sweat of people. So all these rooms are controlled to really get out all the water. So before transferring the coils now into this dry room, there's normally this vacuum drying process and making sure to really bake out the last bit of water. So the foils are basically pushed on a special goods carrier into those vacuum ovens, and then they are stored there on a controlled environment for many hours, 12 to 30 hours, before then transported really into the production of the battery assembly process. So any residual moisture or solvent can be reduced out of the coils. This happens by evaporation. If you decrease the pressure, the dew point also decreases, so it's easier to evaporate liquids under low pressure, but you still can use then additional temperature to bake out the last bit of solvent and water. So normally it works as a system where after the production processes you'd have directly a connection to the dry room, so you don't move the dried coils again into a not dry environment. And that's like a system used here. So how does it work specifically? The chambers are evacuated from air, so the pressure is reduced, and then heated up for 120, 160 degrees for 12 to 30 hours. And under the low pressure, the water boils up easily, and essentially you want to have no residual moisture coming out of the coils in this process. Normally you then can also flood the chamber again with inert gas to avoid adding again some new air. Large systems also have different chambers where you have different segments and inlets and conditioning chambers to pre-warm, starter vacuum, a main vacuum chamber, and an intermediate lock between those chambers before transporting it then into the dry room. Sometimes, in this case, we use here a batch process where the coils are separately put in the oven and then transferred into the dry room. Sometimes you also see continuous systems where, for example, the slitting is directly connected to the vacuum drying, but of course here it gets more complicated to handle both the slitting, cleaning, and then drying the PEP. So all this gives additional challenges to the system itself, but it can be seen that there are different continuous dryers used, and also different technologies. Again, you can use infrared drying instead of convection drying here again, or a combination of both to increase the temperature and the impact of the drying. You also want to make sure that the coil not just is dried from the outside. If you can imagine a big coil, it's easier to dry the outside than the core of the coil, and you want to get the moisture out basically everywhere. So basically we have our first baking process here, using our cut dough, baking it for a few hours. It's not yet the finished dish. That will happen then in the electrode production, but you can imagine that again here it's important to have a good energy and constant energy flow, and ensure that there are no breaks within the energy supply, to ensure that there are no breaks in the drying process. That can happen, for example, overnight before then loading the materials for the morning shift in the electrode production, which we will cover in our next video. So I think we have seen a lot of the battery production steps here in the battery mixing, coating, calendaring, drying, slitting. I think we covered a lot of processes in the electrode production. I will summarize it also for you one more time and give you a little bit more insights here in the next few minutes. But before doing so, I will show you this slide here to display again the differences between a batch process and a continuous process. I will leave you to that, read it a little bit, and then I will give you also a few pictures of vacuum dryers from the industry. So as discussed, here an example of a vacuum dryer with an airlock system to avoid any additional contamination and ensure you can create a nice vacuum with a low dew point. So I think you have seen now everything important for the electrode production. Once again, I will summarize what you have learned, give you a little bit more insight and connect it also to all of you. So we are at an end of an interesting section of the battery production, the electrode production, almost an hour. Wow, it flew. For me, it was very nice to talk about and explain you the different processes here. I hope you also learned something and gained an insight in this super interesting, important process of battery cell production. We covered, first of all, the system of a battery cell, before then explaining the production process of the mixing, how important it is to mix and disperse the raw materials, both for the anode and cathode. Very good. Before then, coating it on the anode foil, the copper foil, and the cathode, the aluminum foil, separately, and then making sure the slurry is evenly distributed on the foils before then very good dried and avoiding any particles. Then feed into a calandering process to really create the right porosity and thickness of the coating, and then creating with the slitting process fitting coils for the later on production or cell assembly, which we will cover in the next video, and then having basically the vacuum drying as an handover process from the electrode production, ensuring the right or missing moisture and solvent in the battery coated electrodes before moving then in the next production process. Of course, you also have seen that this is not a simple process. It's very complex, requires a lot of investment. It's very capital intensive, but also labor intensive, high tech necessary, and a lot of energy consumed also, especially in the drying processes. And a lot of key knowledge happening here in the mixing and coating. So what are the challenges now for you guys if you want to set an electrode production facility up, let's say in Africa? I think, of course, access to the machinery is important, mixers, coaters, to the knowledge, but then also having a good power supply, allowing the dry rooms, the clean environment, making sure you have the right systems in place to handle solvents like the NMP or different binders like the PFDF, which might currently be still imported. On the same side, skilled labor is a very important factor. You need not just engineers, but also technicians to operate the equipment, making sure to work with mistakes, run and maintain them. This sophisticated equipment, this high investment intense equipment. And I think there are still a lot of opportunities, of course, around in this technology. So some advantages could be, for example, that the raw materials are already there. Yeah, so the DRC produces up to 70% of world's cobalt already, which is a key component, especially for the NMC and the cathode formulas. South Africa is the largest manganese producer with NMC and LMO cathode formulas. Countries like Mozambique, Madagascar have rich graphite deposits for the anode production. And instead of exporting all those raw materials, I think there are opportunities to create value chain already within Africa to produce the raw materials necessary for the mixing, like graphite, but also fully coated foils I could imagine being happened in Africa to reduce costs locally associated with shipping back and forth the batteries. I think it might seem now a bit ambitious, but I know that there are factories being built or planned in countries like Morocco, South Africa, Rwanda as we speak, and the demand is huge. Yeah? And I think it doesn't make sense to ship batteries, but rather produce them locally where they are needed. And I think all the African nations have a huge interest in creating local value chain. There are pilots being placed, so I think we have a huge future here, and it's great that you watch this and want to learn and are engaged to create local value and impact. So I would love to learn about your perspectives, your ideas for the local value chain in Africa. And I hope with this lesson I could teach you a little bit insights in the production processes. Of course, it could be only a small glimpse. I could explain the most important parameters in the production processes, could show you a few examples of different technologies, a few videos and insights into battery production, and the different requirements which are also impacted for the equipment surroundings, the factory environment. So I do hope that you all stay tuned for the second video, and ultimately we can work all together that we create an important factor here in the value chain locally with you guys. And I would love that, yeah, out of this electrode production, we take now a look a little bit deeper what to do with this coated electrodes, how to really make out of those a cell. This will be explained in the cell assembly process. Very different perspective here. It was more chemistry, process technology, baking, basically mixing. Now it's about really the mechanical stuff, the assembly, making it correct, you form the right geometry, making sure to build all the pieces correctly together. So stay tuned for the next video. Thanks for watching and see you soon.